Please find your seat. Okay, so before we start the technical program on the second day, just two quick announcements. One is it is highly recommended to wear your mask. Also, it's not mandatory, but certainly highly recommended. And second, please silence your phones during the technical sessions. And yeah, that's it for me this morning, and I turn it over to Yiguang Yu from Princeton to introduce this morning's plenary speaker.
Good morning, dear colleagues and students, ladies and gentlemen. I'm Yiguang Yu from Princeton University. It's my great honor to introduce today's plenary speaker, Professor Deanna Lacoste from KAUST. And combustion at its crossroad today, many people say. If I could allow me to say one thing that could be a game changer for combustion, I would say one word: plasma. If you ask me who is the best person to speak on plasma-assisted combustion, I would give you a name, Professor Lacoste. So this morning, we are so pleased to have Professor Lacoste to deliver a plenary lecture on plasma-assisted combustion. Professor Deanna Lacoste received her PhD in combustion science from University of Poitiers in France, 2002. From 2003, she started her work on plasma physics, plasma-assisted combustion at École Centrale Paris. In 2014, she joined KAUST. She's now associate professor in mechanical engineering at Clean Combustion Research Center at KAUST. She's also associate editor for Proceedings of Combustion Institute. She has made distinguished contributions in many frontiers, including plasma-assisted combustion, plasma discharge, plasma dynamics, and plasma-assisted detonation. Please join me to welcome Professor Lacoste to give her plenary lecture. Thank you. Welcome. The floor is yours.
Thank you, Yiguang. Is it working? Can you hear me? Yeah. So thank you very much, Yiguang, for the really nice introduction. And thanks, Niels and Benedict, for giving me this opportunity. I'm really honored to be here today. I would like to start this presentation with a short video illustrating the research I'm doing in flames with plasmas. In this video, you will see a flame that will be reacting to music. And at one point, the flame will stop moving. And if you look carefully, you will see at the base of the flame a pink light. And this pink light is the plasma. But let's watch the video. So by the end of this presentation, you will understand how it works, how the plasma stop the flame to react to the music. My second objective for this presentation is to give you an overview of all the important results that have been obtained in plasma-assisted combustion over the last 20 years. But before I start with the scientific content, I would like to thank Christophe Loh from Central Supélec and Jonas Mock from NTNU. Both of them have been co-authors on many of my papers, but more importantly, they had a really strong influence on my research. Thanks to Christophe, I discovered the fascinating world of non-equilibrium plasmas. And thanks to Jonas, I discovered the world of flame dynamics. I also would like to thank several of my collaborators, and more specifically those that have been contributed to the result I'm going to present today. So I would like to cite Amar, Anne, Minsuk, Davide, Francesco, Andreas, Joshua, Thibaut, Sylvain, Guillaume, Yuen, and Da. And I also would like to apologize. I would like to apologize because I could not put all the interesting results in plasma-assisted combustion in this 1-hour presentation. On this map, I put in pink color the countries where paper on plasma-assisted combustion have been published. This represents more than 1,000 papers. So our community is growing, and I had to make choices. So sorry if I didn't put your important result. As I said, I had to make difficult choices. So this presentation will have 4 parts. First, I will start with a brief introduction about gas discharge physics and plasma. Then, even if you're not an expert in plasma, you will be able to follow the other part of the presentation. After that, I will give an introduction of 3 of the most common non-equilibrium plasma sources that are used in plasma-assisted combustion. Then I will give a review about what we have obtained, what we have achieved in plasma-assisted combustion. And finally, I will focus a bit more on the work that I'm currently doing, which is the control of combustion instabilities by non-equilibrium plasma. Let's start with the gas discharge physics. And let's start with this question: what is an electric discharge? An electric discharge is a process of turning a gas into a conductive media by applying an electric field. How does it work? Let's take this simple example where you have 2 flat parallel electrodes, an anode and a cathode, and in between you have some gas. On Earth, at atmospheric pressure, the concentration of electron is about 1,000 per cubic centimeter. So when you apply an electric field, you will accelerate the electron, and these electrons, at one point, they will collide with molecules or atoms. And if they have enough energy, they will be able to ionize the gas. Then you will have a positive ion that will be accelerated in the direction of the cathode, and the electron in the direction of the anode. So these 2 electrons will again collide with molecules, and again, if they have enough energy, they will ionize. And this process continues. It's usually called an avalanche. On the head of the avalanche, you have electrons, and on the tail of the avalanche, you have positive ions. If the gap distance is large enough, this process is not happening in a single point in between the electrode, but in multiple areas. And then this avalanche, they grow, and eventually you have electrons reaching the anode, and finally the ions reaching the cathode. And if the ions, they have enough energy, they will be able to extract secondary electrons from the cathode. And then you have media where you have positive charge, negative charge, and this is a conductive media. So here we already have a discharge that's happening. So what I just described is called a Townsend breakdown mechanism. It has been proposed, it was the first explanation of a gas discharge. It has been proposed about a century ago. In plasma-assisted combustion, we don't have so many of this type of breakdown. We have mainly positive streamer breakdown, where you have a small filament that is propagating from the anode to the cathode, or a negative streamer, where you have a small filament that is propagating from the cathode through the anode. There are other types of breakdown mechanism, but these are the most commonly encountered in plasma-assisted combustion. And in the same way that there are different types of breakdown mechanism, you also have a large variety of electric discharges. The type of electric discharge will depend on the electric field intensity, duration, and if it's continuous or if it's oscillating. It will also depend on the electrode geometry, the material, the gap distance, and it also depends on the gas composition, the level of pre-ionization, the temperature, the pressure, and the flow. And if you change any of these parameters, you can completely change which type of electric discharge you are obtaining. So we have this conductive media, and this is usually called a plasma. So then the second question is, what is a plasma? A plasma is a quasi-neutral gas of charged and neutral particles that exhibit collective behavior. I don't want to go into the detail. We find plasma on our daily life Typically in this example, a flame is a plasma, a lightning is a plasma, and if you have neon light in your office, like in my office, then you also have plasma in your office. There are two big families of plasma. You have the hot plasma, for which the temperature is about 1 million or higher than 1 million of Kelvin. On Earth, you find them mainly in tokamaks. And then you have the cold plasmas. And the cold plasma, you have a temperature that can be as high as hundreds of thousands of Kelvin. So from a human perspective, a cold plasma can be quite hot, okay? But it's called a cold plasma. Electrical discharges only produce cold plasmas, like in this example where you recognize a spark plug with an arc. So we have a cold plasma that is produced by our electric discharge. Here again, we have two families of cold plasma. First, we have the equilibrium plasma. Equilibrium means thermal equilibrium. All the particles of the plasma have the same temperature, and they follow a Boltzmann distribution at the same temperature. So the temperature of the electron is the same than the temperature of the ion, and the same than the temperature of the neutral particle. In this example of the arc that is produced by the spark plug, you have an equilibrium plasma. If you do that in air at atmospheric pressure, the temperature will be around 6,000 Kelvin. 6,000 Kelvin, it's a lot. You don't need to have a hot spot of 6,000 Kelvin to ignite a flammable mixture. But this is what we have been using for more than a century in all of the gasoline engine cars. Why are we still using this non-efficient source of ignition? It's because it's extremely easy to obtain an equilibrium plasma. If you apply a DC electric field, eventually this is what you will obtain. So to avoid thermalization, this is another story. So when I'm saying that you apply a DC electric field, a continuous electric field, you have to apply the electric field for more than a millisecond. So from a plasma time scale, a millisecond, it's already a really long time. The second family of cold plasma are the non-equilibrium plasma, the non-thermal equilibrium plasma. So in this kind of plasma, all particles have different temperature. Typically, the electron, they have a really high temperature, and the neutral particle, they have really low temperature, anywhere between ambient temperature and up to a few thousands of Kelvin. Another important feature of non-equilibrium plasmas is that if you want to describe the state of a molecule, you need to have 4 temperatures. You need to know the translational temperature, or the gas temperature. You also need to know the rotational temperature, the vibrational temperature, and the electronic temperature, because all of them can be different. And as I mentioned, to obtain this non-equilibrium plasma, you need to have specific sources that I will introduce in the second part of my presentation. But before that, I would like to say a few more words about the plasma chemistry. So we are all aware about the type of chemistry that we have in combustion. Here for plasma, it's a bit more complicated. We have 3 classes of reaction. The first one are the electron impact reactions. So I just described in the breakdown process that the electrons are the important particles that start the process. And you can have a lot of different types of electron impact reactions. The first one is the excitation. If you have an electron that is not really energetic, then by collision with molecules, you can have excitation of the rotational state, the vibrational state, or the electronic state. Here I put just 3 reactions, but in reality it can be tens or hundreds of different reactions. By electron impact, you can also have dissociation. You can also have a reaction of ionization. And finally, if you are in electron-neutral gas, you can have attachment on the molecules. The second class of reaction are the ion reactions. So here, the ion, the positive ion, they can have a recombination reaction. You can also have electron detachment, associative ionization, where you have 2 molecules that are in the excited state, for example, electronic excited state, that will collide and produce an ion and an electron. And finally, inside the plasma, not talking about combustion, then you have neutral particle reactions. So these reactions, they are really similar to what we have in combustion, even so you don't have combustion or oxidation necessarily happening. So all of these types of reaction, they will have different types of reaction rate. So for the neutral particle reaction, typically the reaction rate, they follow Arrhenius law as a function of the temperature, similarly to what we have in combustion. But for the electron impact reaction, the temperature of the gas doesn't matter much. What will matter is the energy, the acceleration that can have the electron. So for that, the reaction rate, they also follow typically Arrhenius law, but as a function of the reduced electric field. The reduced electric field is the electric field E divided by the neutral density, the number density of the neutral particles N. And in between, for the ion reaction, it depends. The reaction rate can be a function of the temperature of the electron, the temperature of the gas, or both. So let's say a few more words about the electron impact reaction. And here I put on this graph an example of the fraction of the dissipated energy of electron as a function of the reduced electric field in air. And you will see that for low reduced electric field, less than 10,000, then the main species that will be produced by electron impact will be vibrationally excited oxygen. While if you increase the reduced electric field, then you can produce mainly vibrationally excited nitrogen. Or if you increase even further, you will produce mainly electronic excited state of nitrogen. If now you move from air to a methane air mixture, the production of by electron impact will be slightly affected. For reduced electric field, you will have vibrationally excited methane, but then for higher reduced electric field, the main species that will be produced by the electron are the vibrational excited state of nitrogen and the electronic excited state of nitrogen. So we see that from the electron impact point of view, or for this part of the reaction of the chemistry of the plasma, having an air or a fuel air mixture doesn't make a big difference. So with that, I will stop on what I wanted to say about plasma chemistry, and I will introduce 3 of the most commonly used source of non-equilibrium plasma. So as I said earlier, when you apply a DC electric field continuously, you will have an equilibrium plasma. If you want to avoid thermalization, then you need to follow one of these 2 strategies. The first one is to limit the current, to control the current. If you control the current, then you cannot have enough joule heating, and then you cannot reach thermalization. So this can be done, for example, by using a dielectric barrier discharge, a DBD. So if I take again the same simple example of the 2 flat electrodes, you do that by just adding a dielectric layer, like in green in this graph, close to the cathode. Then what will happen? Let's say that you have a positive streamer that will start from the anode. When the positive streamer will reach the cathode, the positive ions, they cannot cross the dielectric layer. So they will accumulate on the surface of the dielectric. And at one point, you will have enough charge to have the same potential on the anode and on the cathode, meaning that all the charged particles in between, in the gas, they will not be accelerated anymore by the electric field, so they will start to recombine, and eventually you will have only neutral particles. So then if you stop that, yeah, it's not really interesting. The interesting point with dielectric barrier discharges is that at this stage, you reverse the polarity. So when you reverse the polarity, then all the positive charge that were accumulated on the surface, then they will propagate in the direction of the cathode, for example, as a streamer. And then they will reach, you will have this filament that will reach the cathode, but as you cannot sustain a flow of positive charges because you have this dielectric layer, once all the positive charge has been removed from the dielectric surface, then you don't have a plasma anymore. And this changes in the different state is what is called a DBD. So this is an example of voltage in black and current in blue signal that you have in a DBD that has been used in plasma-assisted combustion. So you can recognize a sine AC wave for the voltage, and for the current, you see some small peaks, blue peaks. These correspond to these discharges that are highly non-equilibrium. So just an example of how you could do that in a practical application. So this was for a study on plasma-assisted ignition, where they used a high voltage electrode in orange that was is insulated, electrically insulated from the surface of the cell by a dielectric layer in green. And instead of obtaining an arc, as usually you have with a spark plug, then they obtain this kind of discharge where you see multiple filaments surrounding the high voltage electrode. So there are other ways to avoid thermalization by limiting the current. Another really commonly used strategy is to use a gliding arc. To obtain a gliding arc, you need to have diverging electrodes and you need to have a gas flow. So when you have diverging electrodes, if you apply an electric field, the electric potential, a voltage, sorry, you will have an electric field that has a direction of these arrows, but in terms of intensity, it will be extremely intense at the shortest distance between the electrodes. So then this is where you will have the discharge and you will have a plasma. But as you, let's say you're applying a DC electric field, then you will reach an equilibrium. You will have an arc, you will have a plasma at equilibrium. But then this is where the gas flow comes. The gas flow will push the discharge in the upward direction, and doing so, due to the diverging geometry, you will have the length of the discharge that will increase. And when you do that, you will have a higher heat exchange between the hot discharge and the cold gas surrounding the discharge. So then if you want to keep the same temperature, the thermalization, you need to have a power supply that increases the number of electrons that you can flow into your discharge. But then at one point, it will be limited by your power supply. So then when the filament becomes too long, then you start to have a non-equilibrium state, meaning that the electrons, they are at high temperature, while the neutral particles, they start to have a temperature that is lower. So then the plasma filament continue to progress due to the gas flow, still non-equilibrium, and at one point, it will become so long that the power supply will not be able to sustain even the energy of the electron. So at this point, the plasma stops, and the process repeats itself again, ignition and then propagation. So this is an example of voltage and current waveform that has been used in plasma-assisted combustion by gliding arc. And this is an example of a geometry that you can use with a burner, for example, completely made of dielectric material, and with two electrodes with this specific shape, diverging shape. And you have a vertical flow of air that will be used to push the discharge and a tangential injection of fuel. And these are the two examples of picture where you have a flame that is stabilized by gliding arcs. So you can see the length of the gliding arc can be quite large. So these are the two examples where you can avoid thermalization by limiting the current. The second strategy to avoid thermalization is to stop the voltage just after the breakdown. During the breakdown, you don't have the time to reach equilibrium. If you stop just after that, then you will avoid thermalization. So a common way to do that is by using nanosecond repetitively pulsed discharges that I will call NRP discharges. How do you produce them? You produce them by applying high voltage pulses, so high voltage in the range from 5 to 100 kilovolt, short duration pulses in the range 1 to 100 nanoseconds at high repetition rate in the range 10 to 100 kilohertz. So this number, just to give you an idea, but you can be out of this range and still have NRP discharges. What is interesting here is that by varying any of these parameters, the pulse duration, the pulse repetition frequency, and the applied voltage, you can completely change the property of the discharge that you are obtaining, the property of the plasma. So we have been studying this type of discharges in air quite intensively. And here I give an example of a summary of some of the important results. So in this really famous picture from this paper from David Pye, keeping constant the pulse duration and the pulse repetition frequency by increasing the applied voltage, you show that you can obtain 3 different regimes of discharge: corona regime, glow regime, and spark regime. And in plasma-assisted combustion, we have been using both the glow regime and the spark regime. So if you look at this picture, they look quite similar. You can see that the spark regime is just a little bit brighter, a bit more intense. But in terms of what they are doing on the gas, they are really, really different. So if we compare them, in terms of energy per pulse, for the glow regime, the energy per pulse is really low, less than the 100 of microjoule, while for the spark regime, you can have an energy per pulse as high as 20 millijoule. In terms of gas heating, it's also really different. For the glow regime, you have a negligible gas heating, while for the spark regime, you can have strong gas heating with a gas temperature that can reach up to 4,000 Kelvin. And finally, in terms of chemical actuation, we can have up to 5% of dissociation of molecular oxygen by using the glow regime, while with the spark regime, we can have up to 50% of dissociation of molecular oxygen. If you look again at this diagram about the electron impact reaction as a function of the reduced electric field in air, NRP discharges, they are in this area. So during the pulse, during the 10 nanosecond or during the few nanosecond duration of the pulse, the main chemical species that will be produced will be vibrationally excited nitrogen, electronically excited nitrogen, or you will dissociate molecular oxygen. But then after the pulse, what's happening? So if you look, when you stop the pulse after, let's say, 10 nanoseconds, then the main reaction, especially of interest for combustion, will be the reaction of electronically excited nitrogen with molecular oxygen that will produce oxygen atom and some heating. If you look at the longer time scale, typically in the range of 10 or 100 of microseconds, then the main reaction that will happen will be the vibrationally excited nitrogen that will collide with any molecule in the gas to produce some heating. Okay? And if now you focus on the on discharges for reduced electric field that is larger than 100 Townsend, then Nikolai Popov proposed in 2001, so more than 20 years ago, that the two main important reactions that will happen for NRP discharges are these two ones. By electron impact, you will excite the electronic level of nitrogen. Then, after the pulse, the electronic state of nitrogen will collide with molecular oxygen to give atomic oxygen and heating. And he called that the two-step mechanism of fast gas heating and atomic oxygen production. And we spent a lot of effort to try to see if this model was a good model for NRP discharges or not. And this is a summary of some of the results that we have obtained. The short answer is yes, it's a good model. So if you look at the upper graph, it is a voltage. So you have a voltage pulse of 10 nanoseconds. So again, this is at a repetition rate of 10 kilohertz, but I'm just showing for one pulse. Then we measure the temperature evolution during this pulse. So we have an increase in temperature from 1500 to 2500 Kelvin. The atomic oxygen that was measured by Talif did not increase during the pulse, but just after the pulse, you have a strong increase in the concentration of atomic oxygen. And in terms of the electronic state of nitrogen, you are producing them during the pulse, and then after the pulse, you have a decay that corresponds to the increase in the production of oxygen. So this was an experimental proof that the model that was proposed by Popov could be a good model for plasma-assisted combustion. Here there is an interesting result. If you look at the evolution of the temperature, you have an increase by about 1000 Kelvin within 20 nanoseconds. So this is definitely a constant volume heat addition, a constant volume gas heating. And when you have that, you can expect to have some hydrodynamic happening. So this is what we tried to visualize, and we did that a few years ago by using Schlieren visualization. So if you look at the discharge, just at the end of the discharge, you still see the light emission, the white filament. 15 nanoseconds after the discharge, you start to see expanding gas, so heated gas that are expanding after the heating. And if you look even a bit later, at 3 microseconds, you can start to see the shock waves that are propagating from the spark source. So if I summarize, for non-equilibrium plasma discharges, this is not only for nanosecond discharge, but in general, for non-equilibrium plasma, you can have different effects that can be useful for combustion. The first one is the radiative effect. You are producing a lot of UV light and visible light. You can have a chemical effect with production of atoms, such as atomic oxygen, atomic hydrogen, and others, excited species, but also molecules, such as NO, CH3, or ozone, for example. You can have a thermal effect with a fast gas heating, or a slow heating, or both. And then you can have a transport effect. When you have these shock waves and this gas expansion, of course you have a transport effect. But even if you don't have a strong thermal effect, by the fact that you are changing the chemical species, then you are changing the diffusion rates. So you are changing also the transport properties. In plasma-assisted combustion, it is considered that the radiative effect is negligible. So the three main effects that you can have will be a chemical effect, thermal effect, and or a transport effect. Finally, in terms of plasma characteristics, here is a summary of the electron for different types of plasma, what are the electron temperature in electron volts, so the energy of the electron, and the electron number density. And you can recognize the flame that has a relative low electron number density and a low electron temperature. And if you look at the green shape, this is for nanosecond discharges. This is for NRP discharges. And you can see that with this type of discharge, you can have high electron temperature, high electron number density. And also, more importantly, you can have a larger range. So then you can have a lot of flexibility in having different types of plasma. So this is why I'm interested in using these discharges, because they are really promising for application. Another important aspect is that you know when the discharge will happen. You know that the discharge will happen during these 10 nanoseconds. So for all the optical diagnostics, it helps a lot compared to some other strategy where you don't know exactly when the discharge will occur. Okay, so now I will start to give a review about the important results that have been obtained in plasma-assisted combustion. I will only consider three topics. The first one will be on ignition. The second one will be on flame velocity or acceleration of flame velocity. And the third one will be on enhancement on the lean blow-off limit. So let's start with ignition. People have been starting to work on that about 20 years ago. And the idea was really first to have a proof of concept that we can use non-equilibrium plasma to ignite flammable mixture in a way that are comparable to the usual traditional spark plug. So we did that typically in simple system in constant volume combustion chamber. And this is one of the first studies that has been published in this topic. It was for ignition of propane and air with NRP spark discharges. And we showed that we could ignite different equivalence ratio or dilution rate of this mixture at pressure up to 2 bar with a minimum ignition energy that was relatively satisfactory with less than 1.5 millijoule at 2 bar of pressure. So this was one of the early studies. People have been still working on this topic to be closer to a realistic condition. Here it's another example where we compare the propagation of the ignition kernel, of the flame kernel, on the top row for a conventional ignition system, a regular arc, and the lower row for NRP spark discharges. And we see that at 10 bar, for propane-air stoichiometric mixture, we have a larger ignition kernel or flame kernel when we use these NRP spark discharges. So they are a better ignition source than the traditional spark. The community are also be interested in being closer to a real application. And here, for example, I will start with this example that has been, this study that has been obtained in a 4-stroke gasoline engine, where they compared ignition by a nanosecond discharge of 25 nanoseconds with a regular spark plug. And they show that the heat release rate was much higher and faster than with the NRP discharges, with the nanosecond discharge compared to the spark discharge. Another important study was this study from Do et al., where they investigated how NRP discharge could enhance the ignition in a scramjet. Here you have an injection, a tangential injection of a hydrogen in a supersonic flow of air, and they compare, they measure by PLIF the OH signal for autoignition on the left on the A panel, and when you use NRP spark to assist the autoignition, and they demonstrate that the ignition was much more enhanced when you are using NRP discharges. So, as I said, these are two examples of people working to get closer to application. We also had people who are interested in better understanding the plasma-assisted combustion chemistry, and they focused their work on investigating the ignition delay time in shock tubes and in rapid compression meshing. And by comparing the ignition delay time of autoignition and of ignition by nanosecond discharge, they could have idea about the chemistry. So in this example, it was for ignition of ethane, oxygen, argon in a shock tube by using a volumetric nanosecond discharge. And if you look at, sorry, I don't have a pointer, so I cannot show you. But if you look at the white star, these correspond to the autoignition delay. You can compare them with the black star that correspond to the ignition delay when you use the nanosecond discharge. And the first result of this study that by using nanosecond discharge, you can decrease by more than an order of magnitude the ignition delay time. More interestingly here is that they have proposed a chemical kinetic model to try to describe what's happening with the plasma. And they demonstrate that to have the best agreement with the experimental result, they had to take into account the dissociation, but also the heating. And they proposed a model that that was corresponding basically to the model proposed by Popov. So this story of chemistry of plasma is really important because for all the people interested in a numerical simulation, or even all the community, there are many stuff that we cannot measure, and we really need to have this combined effort, experiment and simulation. We need to have good plasma model, good plasma chemistry model. And this is quite challenging because, as I mentioned at the beginning of my talk, the plasma chemistry can be quite complicated and difficult to implement in our combustion simulations. So here I will give a small overview of some of important results that have been obtained. This is a really recent result where they develop a plasma-assisted combustion model with 71 species and 680 reactions. It was for ignition of methane and air. And it's a 0D simulation, and they compare with a measurement of atomic oxygen that was done more than 10 years ago. And they reach a really good agreement for a single nanosecond pulse. So when you are using a single nanosecond pulse, then you can afford to have this relatively detailed chemical kinetic for the plasma. But then if you want to have 1D, 2D simulation, or with multiple pulses, it's a bit more complicated. So for example, here, I show you an example of a two-dimensional simulation of a single, again, nanosecond discharge in hydrogen and air with a chemical model where you have 13 species and 30 reactions. Here I'm showing the concentration of water 30 microseconds after the beginning of the ignition. If now you want to do some simulation when in addition to the two dimension, you also have, for example, turbulence. In this really famous paper from Castella et al., they took a phenomenological model for the plasma coupled with regular combustion chemistry. So this was two-dimensional simulation of NRP sparks, so not just a single nanosecond pulse, but multiple pulses for a methane air turbulent flow. And more recently, yesterday actually, Nicolas Barléand presented a study it was a two-dimensional simulation of NRP glow discharges in methane and air with a relatively detailed plasma-assisted combustion chemistry with a bit less than 50 species and more than 400 reactions. And this is a temporal evolution of the temperature field. So this coupling between the chemistry of plasma and the chemistry of combustion is ongoing. There are some good results that are happening, but this requires more effort. So that is what I wanted to say about the ignition. Let's move to the burning velocity. So for enhancing the burning velocity, you can have different strategy. I would like to start with this example of enhancement by chemical effect. Again, a really famous paper from Umbrello et al., where they enhance the burning velocity of a non-premixed propane flame by using DBD discharges in the stream of oxygen. And doing so, they were producing ozone. So they were actually enhancing the burning speed by using ozone produced by dielectric barrier discharges. And they showed that they could enhance or increase the burning speed by up to 8%. Another strategy is to enhance the burning velocity by a thermal and a transport effect. And this is a recent work that we have done at KAUST, where we tried to accelerate a turbulent flame of hydrogen and air in order to reach a transition from deflagellation to detonation. So this is a picture of the discharges in air, not in the flammable mixture. And we demonstrated that we could accelerate the turbulent flame by these NRP spark discharges at 100 kilohertz. The interesting aspect here is that in this paper we show that this acceleration was actually produced by the interaction between the shock wave produced by NRP spark and the leading shock ahead of the turbulent flame. So these are two examples that you can have different strategy and it's working in enhancing the burning velocity. Let's now show see a few results about the enhancement of the lean blow-off limit. So again, different strategy working also. Let's start with some of the pioneer studies about the enhancement by thermal and chemical effect. So in this paper from Pila et al., on the left part of this graph, you see a flame that is confined on the recirculation dome of a bluff body. And if you apply NRP spark discharges in the center of the bluff body, then you can have a fully developed flame, as on the right part of this figure. So this was a demonstration that you can enhance the lean blow-off limit. We did that for a larger range of velocities. This is a stability map. The red line corresponds to the lean blow-off limit of the flame without plasma. And when we apply a plasma, such as in the picture, you can see that the lean blow-off limit is extended. It corresponds to the pink line at the bottom part of the graph. You can also enhance the lean flammability limit by using a plasma that promotes the chemical effect. And this is something that we have done recently at KAUST by considering a methane air flame at pressure at 5 bar and by using NRP spark discharges. So here you can see an example of a flame at 3 bar that is unstable. It's jumping, it's about to blow off. But then when we apply NRP glow discharges, you can see the flame is still a turbulent flame, it's moving, but it's not about to blow off, it's fully stabilized. And if you look at the base of the flame, you can see the pink filament that are the glow discharges. So here, this is a stability map of the flame without plasma as a function of the pressure, something really traditional for the community. If now we apply NRP glow discharges, we can extend both the stability limit and the blow-off limit over the entire range of pressure considered. And we obtained this good result with a plasma power that was about 0.3% of the flame thermal power, so with relatively low energy deposition. We were not the only one reaching this kind of result with plasma promoting the chemical effect. Recently, Kim et al. Published a paper where they were using dielectric barrier discharges on methane air flame at atmospheric pressure. And here the stability map is a bit more complicated, but if you look at this point where you have a stable flame, here you see how looks the stable flame when it's fully developed. You can see also the location of the electrodes. The grid is one electrode outside of the quartz tube, and inside of the burner you have the bluff body that is also an electrode. If you decrease the equivalence ratio, without plasma you have a flame that is about to blow off, that when you have the plasma you can see the violet color, then you can fully reattach and stabilize the flame. And if you decrease even further, then without plasma you don't have a flame, and with the plasma you can sustain a flame. So as a summary for this review, plasma-assisted combustion, it's working. So you can, if you use a plasma You can more or less do whatever you want with the combustion. It will be working. But we are still investigating how is it working. So we know the mechanism of the plasma action. We know how the plasma could affect the combustion. But we still don't know exactly the coupling between the combustion and the plasma. And really much more work is needed. So to answer the simple question, for this specific application, which kind of plasma will be the most efficient, and where should I put the plasma in my system? These are open questions. It's a trial and error basis. So we are not at the stage where we know already, or we are able to predict how could be the most efficient. We have developed tools, we have developed codes, models, experiments, diagnostics. There is a large pool of these tools. They are available, they are working. But now I think what we need is to have a more structured and a more organized approach to move faster, to better understand and to reach as soon as possible the state where we can be fully predictive for plasma-assisted combustion. So I will now move to the last part of my presentation on the control of combustion instabilities by non-equilibrium plasmas. Combustion instabilities, you can have different types of combustion instabilities. In this presentation, I will focus on thermoacoustic instabilities. So tomorrow we'll have a talk on thermoacoustic instabilities, but I wanted to say a few words first for those who are not familiar, then you can understand what we have done. So in general, thermoacoustic instabilities, they happen when you have a coupling between unsteady heat release rate of a flame and the acoustic mode of an engine. In this example, you recognize a gas turbine. In the middle, you have the combustion chamber. In the combustion chamber, typically the flame is at high pressure and it's turbulent flame. So you have unsteady heat release rate. And this unsteady heat release rate will produce some pressure fluctuation. This pressure fluctuation, they are actually propagating and as sound waves. So they will propagate everywhere in your system, and at the boundary of the system, a part of this acoustic wave will be reflected. And on their way back, they will perturb again the flow field and the flame. And when you have a coupling, this is what is called a thermoacoustic instability. So this thermoacoustic coupling can be quite complex, quite challenging. I don't want to go into the detail, but if you try to make as simple as possible, you can summarize it as a feedback loop between the acoustics of your system and the unsteady heat release rate of the flame. And if you want to avoid thermoacoustic instability, then you have two options. Either you change the acoustics, or you change the unsteady heat release rate. And in plasma-assisted combustion, so far we have been only focusing on changing the unsteady heat release rate, so changing how the flame will respond to velocity and pressure fluctuation. So to understand or to investigate how the flame responds to acoustic perturbation, there is a really interesting tool, a really famous tool that is called a flame transfer function. So in the flame transfer function, we are comparing the relative fluctuation of heat release rate with the relative fluctuation of the velocity perturbation. We can express this flame transfer function as a gain, as a function of a gain and a phase. And this is for a given frequency. For the flame transfer function, we will use different frequency and we will cover the range of frequency of interest. So how do we do that? We do that by using typically a loudspeaker put somewhere into the system that will force the flame at a given frequency and a given amplitude. And we will obtain this kind of flame transfer function. So there are two plots. The first one is the gain as a function of the frequency, and the second one is the phase. Just a few more words about that. So for the gain, if the gain is equal to 1, this means that the flame is actually following the velocity fluctuation. If the gain is higher than 1, meaning that the flame is amplifying the perturbation. And if the gain is close to 0, meaning that the flame is not responsive, is not seeing of the perturbation. So you can have any perturbation at this frequency, the flame will not respond. In terms of the phase, this corresponds to the time delay between the response of the flame and the velocity perturbation. So for low frequency, it's close to 0 because the flame is able to follow the perturbation. But when you increase the frequency, then you have some time lag between the response of the flame and the perturbation. Okay, so how can we change the flame response by using electric field or plasma? And the response is yes. The first paper that has been published on that was at the symposium. It was a presentation by Volkov at the symposium in Poland. They didn't use a plasma, they used a DC electric field. So here, they were using a flat flame, a flame stabilized over a porous media, and they apply a DC electric field across the flame front, and they show that they could change both the gain and the phase of the flame transfer function. So they could change the response of the flame to acoustic perturbation that they were doing with the loudspeaker for the entire range of frequency considered. And in this nice study, they obtained this result not by thermal effect, not by chemical effect, but with transport effect. In their case, it was generation of ionic wind. It was not a plasma. They were just actuating the flame as a plasma itself with the electric field. After that, we started to use NRP spark discharges to try to see if we could change the response of the flame to acoustic perturbation. So we did that on a 4 kilowatt methane air flame with NRP spark discharges at 30 kilohertz. Here you can see a picture of the flame and the plasma in the pink color, which is generated at the outlet of the injection tube. And we demonstrated that we can change the response of the flame for the entire range of forcing frequencies. So this was a good result. Here we attributed this result to the combined thermal and chemical effect. But there is an issue with the NRP spark discharges. As I mentioned, with the NRP sparks, you are heating the gas. You can have a gas temperature that can be as high as 2,000, 4,000 Kelvin. And when you heat a gas, when you have air inside this gas, typically you are producing NO. And this is what we measured here when for a pulse repetition frequency of 0, meaning that we don't have a plasma, so for a flame alone, the concentration of NO in the burned gases, so I'm not talking close to the plasma, but really at the exhaust of the system, the concentration of NO was about 3 ppm. But when we were applying NRP discharges at 30 kilohertz, we increased by an order of magnitude the concentration of NO. So this might be an issue when you want to use NRP spark discharges as an actuator in a real system, because you have a lot of regulation for pollutant emission, and this can be, again, a problem. So what I decided to do is to try to see if we could also have an effect of the flame response to acoustic perturbation by using the glow regime of NRP discharges, where we don't have this strong gas heating. And this is what we did a few years ago at KAUST. Here, I'm not working anymore, we are not working anymore with a turbulent swirl flame, because the energy deposition in a single glow discharge is really weak. You have about 100 microjoule per pulse, so you have a few watts of power. And if you have a plasma power of a few watts, you will have no effect on the flame that is a few kilowatts or a few tens of kilowatts. If you want to have an effect, then you need to increase the plasma power. So you have two strategies. The most interesting is to increase the volume of the glow regime. But this was a bit too complicated, and I decided to go back to the fundamentals. So we work with a really small, tiny laminar flame of methane and air with a power that was about 100 times the power of the plasma. And what we decided to compare is how the flame reacts to plasma forcing compared to acoustic forcing. So in this setup, we have a plasma forcing actuation close to the flame, and we have a loudspeaker, and we compare both of them. So this is on the upper graph, you have the forcing signal, different for the plasma and for the acoustic, but you can see that the response of the flame on the lower graph is quite similar. You have a sine response. This is the gain and the phase, in red for the plasma forcing and in black for the acoustic forcing. And you can see that the flame is much more responsive to the acoustic forcing than, it's much more responsive to the plasma forcing than to the acoustic forcing. And we propose an explanation for that. So here we show that with NRP glow discharges, we could change the flame response to acoustic perturbation, and it could be useful for controlling thermoacoustic instabilities. So now let's go to a real problem, real thermoacoustic instabilities, and does it work? The response is yes. We did that in Berlin about 10 years ago by using NRP spark discharges. We were running this burner in an unstable condition, so we had a strong thermoacoustic instabilities at 150 Hertz with a strong pressure peak. And by using NRP spark discharges, we were able to completely suppress the pressure peak. We also, so this was obtained by applying a continuous NRP discharges. We also demonstrated that we can have a closed loop control scheme, and we could either increase the amplitude of the pressure peak or decrease the amplitude of the pressure peak if we change the phasing between the acoustic forcing and, between the acoustic wave and the plasma forcing. So this result, we are not the only one doing that. A few years later, Kim et al. Reproduced our result at atmospheric pressure. More interestingly, recently they published a paper where they could suppress thermoacoustic instabilities at pressure up to 5 bar by using NRP spark discharges. But again, there is this issue, and I'm still considering that NRP glow is the way to go. So we decided to see if we can use NRP glow discharges to actively control in a closed loop control scheme thermoacoustic instabilities. So this is the schematic of the system that we have used. Just we have a flat flame that is stabilized by a wall, and we have the plasma that are generated across the flame. And in terms of plasma actuation, we are measuring the pressure fluctuation, and we apply a gated plasma signal where we can change the delay between the pressure fluctuation and the plasma actuation. We can change the duty cycle, and we can also change the pulse repetition frequency. And here I just wanted to show a video of the flame without plasma actuation. You can see it's strongly moving. It's an unstable flame. And then when we use the NRP glow discharges, we're able to completely stabilize the flame. So this is a movie. It's not moving because it's stabilized. And we obtain this result with a plasma power, which is about 0.8% of the flame thermal power. So if you are interested, Amar Al-Khalifa will present this study on Thursday morning. So to summarize on this part of my talk on control of combustion instabilities, again, it's working, but we are not ready already to go to a real system and to try to see if we can be efficient on a real, for example, on a real gas turbine. So we still have some work to do, and these are the 4 steps that I think we need to work on. First, we need to demonstrate plasma actuation on other types of instabilities. Here, I show you some good results, but it was only for longitudinal acoustic waves, while we know that in real system, you have other types of thermoacoustic instabilities with transverse wave or spinning waves. You have different types. And you also have instabilities that are not thermoacoustic instabilities. So there are a few groups working on that, but we need more effort. Then we need to demonstrate plasma actuation at pressure up to 10 to 20 bar that are realistic pressure for gas turbines. We also need to quantify and control the pollutant emission in plasma-assisted control of combustion instabilities. And finally, we also need to demonstrate plasma actuation for carbon-free fuels. There are a few papers over the last 2 years on plasma-assisted ammonia flames. They are really promising papers where they demonstrated that they could stabilize the flame, whatever. But more importantly, they could decrease the amount of NOx in ammonia flame, which is one of the big deals. So again, it's working, but we need more effort on that. And to finish this presentation, I want to show you again the same video that at the beginning, but I hope that this time, after my explanation, you will enjoy more the plasma effect on the flame acoustic coupling. So this work was funded by CAUS, by the French ANR, and by the German DFG. And if you are interested by our result, and more generally what is done at the Clean Combustion Research Center at CAUS, you can use this QR code. Thank you. Thank you.
Thank you very much. And thank you, Professor Lacoste, for the exciting and wonderful talk on plasma-assisted flame. And I assume that there are a lot of questions and discussions and with Professor Lacoste. I hope you can do it and during the break time or find her during excursion and to have a chat with her. This is a really exciting area. I think that there's a lot of new things coming up, not just in flames, but also in chemical manufacturing and materials manufacturing as well. And this is really, I think, the exciting emerging area. Thank you very much. So with that, I'd like to present a certificate of plenary lecture to Professor Deanna Lacoste for her plenary lecture on flames with plasmas. Thank you.
Thank you very much. Thank you, Yvonne. Thank you.